Não, que não tem problema ou não dá? Tem problema não? Perfeito. Okay, so I'm Milton Jara. I will give the course on Markov chains this summer. And so before we start, I wanted to show you something about cities in Latin America. No? So this is the Google Maps of Godoy Cruz, which is a city in Argentina. And there is something called Plaza de Armas in all cities, in most of cities in Latin America. So here you can see, maybe one less, the Plaza de Armas in Godoy Cruz. Okay, so it has this particular shape that you can see there. And now let's go to Chillán. So Chillán is a city in Chile. Okay, and let's see if we can spot the Plaza de Armas here. So this is Plaza de Armas in Chillán. As you can see, it follows the same pattern, right? And now let's go to another city. This is Trujillo in Peru. So let's try to spot the Plaza de Armas in Trujillo. So where is the Plaza de Armas? So, okay, it's there, of course. As you can see, so now the pattern is even more visible, no? Because there are less trees, and we can see the pattern. So what is the pattern? So the pattern is something like this. So I'm going to draw it oriented in this way. Okay, so that's the pattern that we've seen in all of these cities. Okay, so this is everything I wanted to show you on the computer today. So let's just turn this off. And so, do you know what Plaza de Armas is? Okay, so what is the Plaza de Armas? You can speak whatever language you want. I mean, as a mathematician, this is something you will learn. You have to speak at least 3 languages, otherwise. Disculpa, no te escucho. So it's exactly that. So So I have a friend which is an architect, and he actually told me the story about the Plaza de Armas. So this concept goes back to Roman times. So when Romans were, doing the Roman thing in Europe, they always do. They have very careful planning. No? Okay, so this is very impressive because we own basically all of our civil planning to the Roman times. Okay, so everything about how cities and work that we do nowadays is basically comes from the Roman Empire. So the Romans, they always did the same thing. They arrived to some place, they conquered, etc., and they built a city. Okay, and the first thing they do is that they draw square, which is this Plaza de Armas, to put the armas, the armory there. And it was very important to have a water source there. That was very important. Okay, so you have a water source, you draw square, okay, open square, and then you do a city which is which is like a grid. Okay, so it has streets, straight streets forming square grid. And in the center of this square grid, you have this Plaza de Armas, this place where you put the armory. So the idea is that if the city is attacked, it's very easy to fortify this square in the middle. Okay, so you just close the four corners of the square, and you fortify inside, and you can remain there for a long time because you have the weapons there, you have some food there, and you have a water source. Okay, so that was a very strategic idea, and for some reason, the Spanish preserved this idea, and wherever they went, the Spanish, when they were colonizing Latin America, and they're founding cities, they always did the same. Okay, so they build a city, they put this Plaza de Armas in the middle, and you can see here, this pattern here is reminiscent of the. So sometimes there is there was a fountain here, sometimes not, but the pattern remained the same. No, this circle encircle the fountain, and the square grid with this plaza in the middle, in the center. Okay, so well, very interesting historical fact, but probably now you are asking yourselves what this has to do with Markov chains, no? So the idea where Markov chains enter into the picture here is that now let's imagine we have a guard. Okay, so there is this guard that is guarding the plaza. Okay, so he's doing his rounds at night, and let's say that you are in the so it's not allowed to be in the plaza at night. Okay, because many reasons, no. But you're there, and you want to stay at the plaza, and you want to avoid to be caught by the guardian. Okay, and it's night, so you don't see, and you move around. So the question is, what is the best strategy for you to stay away from the guardian, and for the guardian to actually catch you, no? So find someone who might be in the plaza. Okay? Very surprising fact. So for someone to avoid the capture, the best strategy is to stay still. That's the best strategy. So if you move, you actually have a bigger chance to be cut. Maybe it's the same chance, okay, but maybe moving around might be a strategy as good as to stay in the same place. But now for the guardian, things get more interesting, okay? So what is the best strategy for the guardian to catch someone who might be hiding in the plaza? And the answer is random. And so what you have to do is what we call a random walk. Okay? So what is a random walk? Well, you start here, right? And then you choose one of the paths out of this point at random with some law. Okay? And then if you arrive here, for example, you do the same again. Now you choose one of these three at random. How do you choose exactly? Is a very good question that we will try to answer, okay? So when I say at random, this is not yet completely well defined, because what does it mean at random? Well, here we will assume that probability exists. So let me say briefly about take the time to speak about the prerequisites of the course. Okay, so for this course, in terms of strict prerequisites, the only prerequisite is a previous course in a discrete probability. Okay, something like, but nothing very fancy. Okay, so just a course on which you may have learned about independence and probability. So, for example, counting problems. Okay, so what is the probability of throwing a pair of ones on when you throw a dice, things like that. Okay. And so, but when you do a first course in probability, you usually assume that whatever state space you're starting with, probabilities are uniform. And then you ask questions about things, assuming that probabilities are somehow uniform. Okay, so for example, when you throw a dice, probabilities are uniform in the sense that each one of the possible outcomes of each one of the dice are equally possible. Okay, so one first way to think about the problem is when I say at random here, I had to specify the law. Okay, so let's say that we do it uniformly at random to start with. Okay, so when you say at random, you still have to specify the distribution that you are going to use. Okay, and in this case, let's think about this problem as what we call the symmetric random walk, which means that we choose one of these three guys here uniformly at random. Okay, if you are here, you have 4 choices. Okay, so you choose one of these 4 uniformly at random. Here you have 8 choices, so you choose one of these 8 uniformly at random. I had to tell you that that's not the best strategy. Okay, uniformly at random is not the best strategy. We will see a little bit why. So, okay, so it seems to be a good idea for the guard to do these rounds at random. Why at random? Because if you do it, for example, in a periodic way, you are completely predictable. And if someone wants to avoid the guard, he just has to move periodically in a way of which you never will be crossing with the guard. Okay? So now, so this guard is moving uniformly at random. Okay? So each time it takes step, it chooses one of the possible paths out of the point where he is, uniformly at random. Now that we know this, where should someone hide in order to avoid the guard? Okay, so that's another question. Okay, so this is like is what people call a game in economics. Okay, so it's so you know what the guard is going to do. Now you choose your strategy. Now that you know what the strategy of the person hiding is, you know what it is. Now the guard chooses another strategy, and they keep doing this by turns. And a very classical question in what is called game theory is to see if this procedure converges to a fixed strategy. Okay, this is a sort of important problem in economics. It has to do with this. It has to do with this question about the market, no? Whether the market is really the best way to maximize resources in an economy. So free market, no? As you may imagine, the answer to this question is, well, sometimes yes, sometimes no. So let me do the following thing. So you see that this graph here is very symmetric. So one can make a simpler question. So one question that one can make about this this guard here is that when these guardians start to do this random walk, where is the probability of being in each one of these points here? Okay. So this question is a little bit complicated because there are many points. Maybe we can ask a simple question, no? Which is, what is the probability of being either in the center, in the middle ring, or at the outer boundary of the plaza? Okay, so question. What is the probability of the guardian being at distance, let's say x from the center, where x in this design here, the distance can be 0, 1, or 2, right? It's 0 if the guardian is here, it's 1 if the guardian is on the inner ring, and it's 2 if the guardian is at the boundary of the plaza. Okay? So we can see that if we only record the distance of the guardian to the center, okay, so we have here, let's say, so this is 0, 1, and 2. So if the guardian is at 0, what do we know about the distance in the next step? So in the next step, it's always going to be equal to 1. Okay? So it means that it goes to 0, from 0 to 1 with probability 1. Okay? So if the guardian is on the inner ring, it goes uniformly at random to one of the 4 neighbors. 2 of these neighbors are on the inner ring. So it has a probability 1/2 to stay there. Okay? And it has probability 1/4 to go either to the center of the plaza or to the boundary of the plaza. Okay, now let's see what happens at the boundary. At the boundary, always happens the same thing. You see that you have always 3 neighbors, and 2 of them are at the boundary. So you stay at the boundary with probability 2/3, and then you go to the inner ring with probability 1/3. Okay? So you see that how the guardian moves in terms of distance follows these rules here. Okay? This thing that I just drew here is actually a very popular representation of a Markov chain. Okay, so this is usually how, this is one of the ways on which usually Markov chains are presented. Okay, these schematics here details the rules at which this Markov chain works. Okay, so at each step you choose in a random fashion where to go, and the probabilities, well, you have to do it in a certain way. You see that in this simplified setting, the probabilities are no longer uniform. Okay, so this is why it's always important to distinguish between uniformly at random and at random, because at random it means that there is some randomness, but not necessarily uniform. Okay. Even in this extreme case, one says that this motion is random in some sense. Okay, because the probability is 1 and 0, but it's still a probability. Okay, so this is the dynamics. Now, let's see what happens if you start at the center of the plaza. Okay, so if you start at the center of the plaza, after one step, you are no longer at the center of the plaza, and with probability 1, you are at the inner ring. Okay, so now let's see what happens if you are at the inner ring. If you are at the inner ring, after one step, with probability 1/4, you come back to the center. With probability 1/2, you stay at the inner ring. And with probability 1/4, you go to the outer ring. So now let's see what happens in the next step. Okay, so in the next step, now things get a little bit more complicated, right? So what is the probability of being at the center? So if you are at the center, you go out. So this guy doesn't contribute to the probability of being in the next step at the center. If you are at the outer ring, you cannot reach the center in one step, so this guy also doesn't contribute. If you are at the middle, with probability 1/4, you go to the center. Since you are with probability with 1/2 at the center, we see that the probability is 1/8 here. Okay? So now let's compute the probability of being at the outer boundary of the plaza. So this guy doesn't contribute because you cannot go from the center to the boundary in one step. If you are already at the boundary, you stay there with probability 2/3. So let me, with probability 2/3, you stay at the boundary, and you are at the boundary with probability 1/4. So that's the contribution of this part here. But with probability 1/2, you are in the middle. If you are in the middle, you go to the boundary with probability 1/4. So the probability of going from the middle to the boundary is the probability of being at the boundary, at the middle, times the probability of going. So this is what? It's 1/6 plus 1/8, right? 1/6 plus 1/8. So I will need your help with these things because I'm not very good at math. 24. This is 3/24. This is 4/24, maybe. So this is maybe 7/24. And is it correct? Yeah. Okay. So this guy here is 7/24. This guy in the middle is more difficult to compute because there are many contributions. There are contributions from all the guys. But here we can do some trick, no? Because we know that the total probability has to be equal to 1. Because what is the probability of the guardian being somewhere in the plaza? Is 1. Okay, so the guardian doesn't leave his post, so he's still somewhere there. So here we have to do some computation. So this is 3, 7, 10, 20, 14, 7 divided by 12. Or also known as 14 divided by 24. Right? Okay, so this is after 3 steps. Okay, I'm not going to do the next one because that was it's too difficult. I have it on my notes, but I'm not going to do it. What you can see here is some tendency, no? From these numbers here, you can see that there is a tendency to have less probability at the center. Okay, so that's why I was telling you that it's not a good idea to do this strategy, because the probability of the guardian being at the center is smaller. Well, this is not exactly accurate because these are probabilities of being on the different rings here, no? Because actually the probability of being at this point here, so we imagine the following. So we let this thing here, this random process, this random evolution, run for a long time. Okay, so the guardian, after a few hours or something like that, forgets completely where he started from, and now the question is one interesting, and this is actually one of the most important questions in the theory of Markov chains, is how this probability looks like when you take a lot of steps. Okay, and well, there will be some number, and now what is the probability of this guy here? So what is the probability of the guardian being exactly here? Well, it's going to be the second number there divided by 1, 2, 3, 4, 5, 6, 7, 8. And the same for the outer ring. It's that number there divided by 8. And in the center is just the first number. So you have to compare this guy here with this guy here divided by 8, actually. So if you divide this by 8, you get something a little bit smaller than 1/12. So it looks like actually maybe it's a good idea to hide in the middle. Maybe it's at the outer ring. No, it's a better idea because this number looks like it's going to be even smaller. So this brings to another question, no? So, question. How do these numbers look like after a lot of these steps? So how do these numbers look like after a lot of these steps? Okay? So let me put up here the computation of this number. Now, how did we compute this number? So this number is just 1/2 times 1/4, right? So it's actually so let me rewrite this guy here in the following way. So let me do this, transform this into something a little bit more systematic. Okay. Okay. Well, here it's not strictly necessary to do this, no. But I don't know if you know this this joke, but there is a joke. So how can you stress a room full of mathematicians? You know how to do that? Well, you just write the following. Yeah, this is very stressing for a mathematician. No? There is something wrong with this polynomial, no? I don't know what, but certainly. Okay. So this is how we compute this number here. Okay, the number in the middle. Okay, I will leave it for the last. So this one here, I'm going to add one extra number here, which is 0 times 1/8. Because okay, this one we didn't put into the computation because it's trivial, no? So it's 0. But let's put it back. So how did we compute the 1/8? It's one. It was not 1/8 here. It was 0 times 1/4, no? Yeah. So the 1/8 was 0. So it was 0. So let me write it like this: 1/8. So it was 0. So it was 0 times 1/4 plus 1/2 times 1/4 plus 1/4 times 0. And the one in the middle, this 7/12, is actually is 1/4 times 1/3 plus, so you stay with probability 1/2 and you are there with probability 1/2, so it's 1/2 times 1/2 plus, so the center has probability 1/4 and then you go to the middle with probability 1. So hopefully this is exactly what is written there. Which is, okay? Okay, so this thing here is the computation we did to compute this number here. Well, it's not a number, it's a vector. Okay, so which are the probabilities of being at each one of the possible distances from the center in this random motion around the plaza. But you see that this has a structure, no? Now, if you want to keep going with this computation, well, you can just write a lot of numbers, but there is a better way to do this computation, no? Because if you pay enough attention, now when we want to go from this one to the next one, what we are going to do is that when we are going to replace these numbers here, the 1/4, 1/2, 1/4, by the new probabilities here. And we are going to leave the other numbers, no? The first terms in the multiplication as they are. Okay? So this is actually a multiplication of a matrix times a vector. Okay? So the matrix is 0, 1/4, 0, 1, 1/2, 1/3, 0, 1/4, 2/3, and the vector is the current probability vector. Okay, so I'm going to call this vector here a probability vector because it's a vector on which all the entries are non-negative and the sum is equal to 1. So this is what we call a probability vector. And what we are doing here is just we're multiplying. So if we call this vector here, so how do I want to call it? Maybe I want to call this one here mu0. Then you go to mu1. Then you go here to mu2. And here you go to mu3. And you see that if you multiply this guy here by the vector, okay, so I'm writing there as row, and here I should multiply it as a column, right? So maybe I'm going to, so to keep the notation consistent there, I'm going to transpose this matrix here. And I'm going to multiply by the other side, no? So then it's going to be 0, 1, 0, 1/4, 1/2, 1/2, 1/4, 1/2, 1/4, and 0, 1/3, 2/3. And now what happens is that if you multiply this by mu t, this is going to be equal to mu t plus 1. Okay? So this is this computation here is what we are doing a little bit by hand here. Okay? So if you call this guy here, it's a matrix. If you call it P, we obtain the following formula. So this formula has a name, okay? It's called the Fokker-Planck equation. Also called Chapman-Kolmogorov equation. And the equation is this. Mu t1, mu t plus 1 is equal to mu t times p, where this is okay, let's keep it like that for the moment. Okay, so this is the equation, no? That so observing the computations we did here to decide where what are the probabilities of the guardian being at distance x from the origin. We saw that this computation can be somehow systemized as with a little bit of linear algebra, okay, as a matricial equation. Okay, each time if you want to know what is the next probability in this sequence there, the only thing that you have to do is to multiply the previous one by the matrix P, where this matrix P is here. So this type of matrix is called stochastic matrix. Okay, and what are the particularities of a stochastic matrix? All the entries are non-negative, and the sum over each row is equal to 1. And what this guy here represents? It represents the probabilities of going from this point here to any of the other points in this drawing here. Okay, you see the first one is not that interesting. The second row, so 1/4, 1/2, 1/4 is exactly 1/4, 1/2, 1/4 is exactly these numbers here, which are the numbers that go out from the point, let's say, x equal to 1. Okay? So if you want to answer this question, so that question there, you can rephrase it in the following way. No? Why? Because if you iterate this formula here, no, from the beginning, so if you start with some vector mu0, mu1 is equal to mu0 p, mu2 is equal to mu0 p squared. So actually, mu t is equal to mu0 times pt. Okay, so here maybe I put a 0. And maybe what you really want to know is the limit of this power here, p to the t. Of course, part of the question is whether this limit exists or not. It's not obvious at all that this limit is well defined. Okay? It turns out that for this matrix there, the limit is exists. Okay? So if you know a little bit of linear algebra, how do you compute the powers of a given matrix? You remember that? So one way to do it is to diagonalize it, this matrix. So let's say ways to compute pt. Ways. So first way, so we diagonalize p. Okay, so let's say that p is the diagonalizable. So are all matrices diagonalizable? Well, it depends on, yeah. Yes, no, yeah, no. But okay, let's assume that this one is diagonalizable. Okay, so this means that you can write this as something like ut du, where u is unitary So it's a rotation, and D is diagonal. Okay, so transpose and T, okay, not a good choice of notation. Maybe I'm going to use U star, okay, so for the transpose. So if you can do this, then P to the T is just equal to U star du times U star du, etc., U star du. And what does it mean a matrix U to be unitary is that this product here is actually equal to the identity. So this is going to be equal to U star D to the T U. Okay? So if we can diagonalize the matrix, it's very easy to find the powers of PT. If we can diagonalize it. Okay? So here, of course, people will complain. Okay, so the mathematicians will complain, and sometimes I don't know if this is the case here. We get some people from applied math and computer science doing the course of Markov chains, because Markov chains are very important in applied math and computer science. So I don't know if. So do we have people from applied math, computer science? Yes. Okay. So everybody will complain about this because there's a problem. People from pure math and applied math will complain for different reasons. Okay, pure math, they will start to tell you about, there is this problem because maybe the Jordan matrix of your matrix is not diagonal, then this decomposition doesn't exist. So this is the type of complaints from mathematicians. No? So is that this is not true. This is not always true. Of course, people from computer science will tell you something very different, which is this is completely unnecessary, because if you really want to compute the power of a matrix, you don't diagonalize the matrix. No, you use. So what is your favorite way to? Okay, so you have so somebody knows how to actually compute in a more efficient way the power of a matrix P. Huh? What? No. Yeah. So what you usually do is a triangular decomposition, because that's way more efficient in terms of computing power, computing cost, than to actually diagonalize the matrix. Okay, so B. So what is your favorite triangular decomposition? Do you have favorite? Somebody has. Somebody knows what I'm talking about? Okay, what is your favorite triangular decomposition? Huh? LU. Okay, so we write P equals to LU. So what does it mean? So this one is lower diagonal, right? So this is lower diagonal. And this one is unitary, no? Is unitary? It's upper. Upper diagonal. Okay? So the idea is that you can use this, because if you do the multiplication, multiplying lower and upper diagonal matrices is very fast. Okay? And this you can always do differently from diagonalizing. So this is better, okay, from the computing point of view. Okay, but I only have chalk, so I cannot do neither, no. So if we would really want to solve this problem, we have to do easier problem. Easier problem. So maybe you know there is another famous joke about mathematicians. No, that this is the mathematicians and the cows. You know that joke? Maybe you know that joke. No, you don't. Okay. So the joke is like this. Okay. So there is a farmer. There are cows, and the farmer wants to improve the amount of milk they can produce. Okay, so they bring an engineer, a physicist, and a mathematician, and they ask him how to do it. No, so they get their plan and they say okay. So the engineer says okay, I can improve it 3%. Then you took okay, yeah, and the physicist no, okay, I can improve it 7%. And then the mathematicians say, okay, I can improve it 20%. 20%. Oh, yeah. So they go to the mathematician and ask, no? So then, how do you do it? No? How do you improve by 20%? And the mathematician started to explain. Well, let's assume that a cow is spherical. So this is what mathematicians do, okay? So they simplify the problem until they get a problem they know how to solve. Once they solve this simplified problem, well, depending on okay, so the idea is that once you solve the simplified problem, you extrapolate, okay? Meaning that you say, okay, the more complicated problem is more complicated to solve, but it will be qualitatively similar to the simplified problem. And then if you are a pure mathematician, you just solve the simplified problem and you're happy. But if you are an applied mathematician, what you do is that you solve the more complicated problem in an approximate way. And if this approximate solution of the more complicated problem looks like the exact solution of the simplified problem, you say that your approximate solution is good. Okay, so you extrapolate. So an easier problem is the following. Okay, so let's go back to the plaza, and let us simplify the design of the plaza. Okay, so now let's take out the inner ring. Here you can argue, no? Usually mathematicians do that. No, you know, the inner ring is actually very close to the center of the plaza, so you can forget about it. But the real reason is, okay, with the inner ring I don't know how to solve it, so let's forget about it. So if we do this, now this problem about the distance to the center gets simplified because now we have only two possible distances, no? 0 and 1. So if you are at, so this is 0 and this is 1. And if you are at 0, you go to 1 with probability 1. If you are at 1, you go to 0 with probability 1/3. And you stay where you are with probability 2/3. Okay? So now we know what we have to do. No, we have to write this matrix P. Okay, so this matrix P is equal to 0, 1, and here you stay put with probability. No, you go from. So this is probability from going to 0 to 1. No. This is from going to 0 to 0, from 0 to 1, from going to 1 to 0. So it's 1/3. 2/3. Okay? And I'm going to write this matrix as 1/3 times 0, 3, 1, 2. Okay? Because I'm way better multiplying natural numbers than rational numbers. Okay? Maybe a computer will agree with me. Okay, so let's see what happens when you multiply p, no? Let's say what is p squared. So p squared is 1/9 times 0, 3, 1, 2. 0, 3, 1, 2. This looks very silly, but let's see what happens. I mean, I'm super lazy. I don't want to do special decomposition, LU, UD, etc. Maybe with a 2x2 matrix, we can just, multiply and see what happens. Let's see. So we get 3, we get 6. Okay, so the 1/9. We get 3, we get 6, we get 2, and we get 3 power 4, 7. Okay, now let's compute the cube. So we get this times this, 3 times 2, 6. This times this, 3 times 7, 21. 1, 3, 2, 2, 4, 7. 6, 2, 7, 6, 7, 14, 6, 14, 20. Is that correct? Okay, there is a pattern, no? You see, this one is repeated here. There is another pattern, no? The difference is 1. Okay, let's do another one. P to the 4, and then there is the 1/27. Well, the 1/27 is easy, no? Because it's just the power of 3. You have 1/81, 0, 3, 1, 2. 6, 7, 21, 20. So this is going to be equal to 1/81 times 21, 6, 20, 60, 61. So from here, you can see clearly that p to the t is equal to 1/3 to the t so this is very clear, no? What it is. So notice that 61 is equal to 81 minus 1 divided by 4 times 3 plus 1. That is 60. Okay. So this entry here is actually 3 to the t minus 1 to the t divided by 4 times 3. Right? Of course, no? And this one is the same plus minus 1. No? 3 to the t minus 1 to the t divided by 4 times 3. Let's see. So if it's an even power, you have to add 1. If it's an odd power, you have to subtract 1. So it's plus minus 1 to the t. And these ones here are the same ones, but with t minus 1. Right? So this one is here is 3 to the t minus 1, minus 1 to the t minus 1, divided by 4 times 3. And this one here is the same thing, no? It's 3t minus 1, minus 1 to the t minus 1, divided by 4 times 3, plus minus 1 to the power t minus 1. Right? Okay. If you didn't find this easier than to diagonalize the matrix, it's okay. Okay, this is something that you can also do. Okay, so if you're not happy with this computation, you can diagonalize the matrix and do the classical way. Okay, but well, the point of all this computation is that when you send t to infinity, here you can send t to infinity. It's very easy. Right? Because you see, I'm divided by 1 to the 3 over t here. So all these 4 limits of this of the entries of this matrix are well defined. So the first one gives you, so the minus 1, this plus minus 1 says actually that don't matter at all. They don't enter into the computation. So we can forget about that. Here you have 3 to the t divided by 3 to the t. That this is just 1, so you get the following matrix. It's 1/4, 3/4, 1/4, 3/4. So now we are super happy, no? I don't know. At least I am super happy. Why? Because what happens with this matrix here? If you plug to this matrix any probability vector from the left, when you do the multiplication, you always get this vector here. Okay, so let's do this observation. Now, observation. For every probability vector let's say mu, what we have is that and let me call this matrix here P infinity. Okay, just to give it a name. Okay, because a probability vector mu is just a vector which has entries p and q, where p plus q is equal to 1, and p and q are not negative. So if you do the multiplication, you see that you will get 1/4 times p plus 1/4 times q, and the sum of p and q is 1, so you get 1/4, and the same here. So you always get the sum times the number. So you get this. Okay? So what happens with the probabilities of finding the guardian somewhere in this plaza at time at a very large time? So the numbers are there. So here is 1/4, and here is 3 divided by 16. So you see that the probability of finding the guardian at the center is a little bit bigger than finding the guardian at one point at the boundary. So if you want to hide from the guardian, what you have to do is to stay at the boundary. Where at the boundary doesn't matter, because the probability of the guardian being there is more or less the same. A very important question. This is something we're not going to do today, because we are going to do it later during the course, is how can we define the probabilities of this guardian moving in such a way that that limit that we did there is actually uniform on the graph. Okay, this is a very important question, which is related to a very important method in applied math, which is called Markov-Chain Monte Carlo, also known as MCMC. Okay, so we are going to see that we are going to study that in some detail later on the course. At that point, at this point, the only thing that I wanted to emphasize is that under very mild assumptions, okay, so there are some assumptions that one has to do, but they are very natural, okay, and simple to verify. Whenever you have a stochastic matrix here, this limit exists, and it's always of this form here. Okay. For the ones that knows a little bit more of linear algebra, what I can say is that under very simple and verifiable conditions, the largest eigenvalue of this matrix P in absolute value is 1, and is a simple eigenvalue. Okay, so it has only one eigenvector up to a constant. Okay, and if that is true, then this limit has to be the matrix on which each one of the rows is that eigenvector. So okay, so that was more or less the introductory part. Well, if you have the patience to do it, you can do the same for the original problem. Okay, you can find the limit of the matrix P for the problem of the distance. The evolution of the distance to the center of the plaza in the original design I drew here. Okay? Okay, so let's do a 5 minutes break. I'll just go to get a coffee. And Então, so now we need to discuss a little bit about something very, I assume, very important for you, which is actually things like the references and the evaluation of the course. Okay? So let's go first to references, okay? So let me verify here. So we are going to use three. There are three basic references for the course. So the first reference is a book. So I'm going to write this reference in inverse order of recommendation. Okay, so and also in a inverse order of difficulty somehow. Okay. So the first reference is a book by James Norris called Markov Chains. So what we are going to do here is cover basically on the first chapter of this book. So this book is not available for free on the internet, but if you go to the website of the Probability Statistics department in Cambridge, there are various lecture notes that are basically based, very based on this book, and there are also some excerpts of the book that covers basically the first chapter. So there are various ways on which you can access this material, and then you can choose whatever source suits you better. Okay. So the second one, it's the book by Levin, Perez, and WILMER called Markov Chains and Mixing Times. So this one is so the PDF file is available for free on the website of David Levin, so you can find it there. You have to check. There are two editions, no? The first and the second edition. So the second edition is slightly more demanding in terms of mathematics, but it corrects a lot of misprints and typos of the first edition. Fun fact about this book there is that if you look at the preface of the second edition, you will find acknowledgement to various former students of IMPA, because when this book just appeared, no? So I think the first time we gave this course here at IMPA Markov chains was exactly the year, well, not the year because it's January, no? The year before this book appeared, and then we start to use it immediately. So we found a lot of misprints and typographical errors, and the students send them to the author, and they actually correct them in the second edition. So you will find the acknowledgement to these students from IMPA. And this is the main reference we've been using for this course for a few years already, maybe 10 or 12 years. But now, it just appeared a new book on Markov chains, which I found very interesting. By Tim Mesipek. Okay, so let me see if I wrote it correctly. No, Mesipek. So it's Mesipek and Sumit Pal. And it's called, how is it called? Finding Markov chains in Monte Carlo. Okay, so this book here is actually only available online. Okay, so there is not a printed version yet. So it's a very nice book. So so this one is very much based on this one here, but it's like an extended version of this book. Okay. So this book here, it goes at the beginning very fast. So sometimes for students that are not super familiar with probabilities, it's a little bit difficult to read. So I believe that this one is better suited if you don't have that much familiarity with probability. So depending on the level of familiarity you have with probability theory, you can go up in this chain of books. So this is the more demanding, this is medium level, and this is entry level. Okay. So during the course, I'm going to loosely follow this book here, but as you will see, there is nothing about Plaza de Armas in either of these books. Okay. So it's very important. So something which is very important. Okay. So these are the references. So I'm going to loosely follow the presentation of this book, but you can read the book you prefer. you can use it to study. So some recommendations, okay? So about general recommendations about the course. The first thing that you have to understand, this is something that most students, especially when you come first time to this summer program at IMPA, you are supposed to follow one course. Not 2 courses, not 3 courses, 1 course, okay? So, in particular, I'm going to assume that all of you are completely dedicated to only this course, okay? Why? Because if you are a master student here at IMPA, or also PhD student at IMPA, the load of the summer program is 1 course. Okay, so master students at IMPA and PhD students at IMPA, they take 1 course during summer. Because that's the courses are constructed in that way. So you of complete dedication to only that course, okay? Which means that you have to study, okay? So, in particular, I'm going to assume that you are going to do a lot of additional work outside the hours of the course, okay? So if you want to get a good grade, you need to work. How are you going to work? So, the main advantage of this book here is that it has lots of exercises. So you are supposed to do lots of exercises by yourself, okay? This one has a good amount of exercises. This book here is more technical. It has not many exercises, okay? And the same way, when you go up in this chain, the proofs get more involved and more general, okay? So this is an introductory course on Markov chains. So what I really expect is for you to do a lot of exercises. So if you had to decide between studying proofs or making exercises, okay? Of course, my lecture will be more focused on proofs. But you also have to do lots of exercises, review the proofs at home. Evaluation. So how is the evaluation of the course? So usually we do 3 exams during the course. Okay, so so let's look at this. So so Carnival this year, so the dates of the exams are always related to Carnival, no? Because that puts some restrictions on what we can do. So Carnival this year starts on February 13, which means that the second exam is going to be on the 12th of February. Okay? So that's the second exam. During this time, okay, so at 8. So there are, until the 12, there are 1, 2, 3, 4. There are 5 weeks until then, which means that a good time for the first exam will be in the middle. So that means 2 weeks and a half from now. 2 weeks and a half from now, it's the 27th of January. Okay? And then a third exam after Carnival. So we do that usually the last day of the program, but since many students leave that day, we can do the 26th, which is a Thursday, not a Friday. Okay? So for the exams, well, you can ask around. The students have usually they compile a list of all their exams, and you will see they are super difficult. Okay, so it is expected for you to suffer during the exam, but if you do a lot of exercises, you're going to get a reasonable grade. That's not bad. But of course, if you want to get a top grade, you have to do a little bit more. Okay. So what I expect is that if you work reasonably well, you will get a reasonably good grade. But if you want to get a top grade, then it's more difficult. So we will have a teaching assistant. So João Pedro is going to be our teaching assistant. So tomorrow I will ask him to come to pass by to set some teaching hours for the course. So exercise list. I don't do exercise list, okay? I don't even give exercise list because this is something that you have to start to learn a little bit. So, as you may know, IMPA is a research center, very well known internationally. Therefore, as a research center, the main focus is research. When you are at the university, courses used to be very well structured, okay? So, lecture, material, exercises, exams, and if you study, then you pass. If you don't study, you don't pass. This is not how research works, okay? When you do research, something that happens a lot is that you do everything well. So you work a lot. So you know you do your fair amount of work. You do your job, and you don't get any result. Okay, that can be very frustrating. But it's an important part of research because quality research involves risk. If you don't take risks, you don't do good research. So my mission, and this is the mission of the summer program at IMPA, is try to introduce you to the world of research. So in particular, I think it's very important to keep that type of uncertainty during the course. What does it mean? It means that you have to figure out for yourself what you have to study. What are the exercises you have to do? What are the books you have to read? What material is more important? What is less important? You have to learn to manage your work. Okay. And one way to force you to do that is I don't do exercise lists. Okay, so you have to do exercises, but you have to figure out what are the exercises that you should do. Another very important aspect of research is collaboration. Okay, something you may notice that there is a coffee room here at IMPA. People think that the coffee room is important because of coffee.
Yes.
Huh?
Yes.
No. It could be tea. It doesn't make a difference. The important part of a coffee room is to gather people together. Because science is a collaborative enterprise. So students have to learn to collaborate, to talk with each other. So it's very important for you to try to talk with each other, help each other, and don't feel embarrassed to ask for help if you're, for example, if you are struggling with some proof, with some exercise. Talk with other people, because this is one of the most important parts of science is collaboration. And this is why we have a coffee room. It's not because of the coffee. It's because it's the place on which you talk with each other. You find other people. Especially because mathematicians has this tendency to be very close. So in particular, if for example, if you if you look at probably at the references, you will see that there are way too many exercises. And then you say, well, what can we do? Well, something that you can do is that you can do some of the exercises and ask other people about the other exercises. No? You have to share your work. Now, this is very useful, and it's very it's something that I suggest you to do. It's very important. Okay. So I think that's what I wanted to say about the technicalities of evaluations and the like. So now let's go back to Markov chains. Okay. So yes. Sim.
João Pedro, a aula dele, o conversa com ele é ad hoc, eu vou lá na sala dele e...
Não, amanhã ele vai passar e vai marcar uma hora para...
Ah, maravilha, obrigada.
So, okay, so let's go back to, yes? You have this formula, no? No, the other way around. Right? So inductively, you can show that this implies that actually mt is equal to m0 times p to the t. Okay? So, because this is actually, so you iterate this formula, you see that this is mt minus 1 times p squared, until you get to this formula here. So that's why this is what we were doing actually in our procedure. No? We are computing the next one as the previous one times p. And if you iterate this formula, this formal formula, you get to this formula below. So you discover that actually, if you want to see what happens after t steps, something that you can do is first take the t power of the matrix and then apply to them to the standard vector. Okay, so let me draw here our Plaza de Armas one more time. Okay, so this is our Plaza de Armas. So, as you may have noticed, this Plaza de Armas is an example of what people call a graph. Okay, so let us define in a more formal way what is a graph. Okay, so definition: a graph we usually use the letter G for graph. And it's a couple V, E. So now let's say what V and E are. So where V is so what it is? This is a non-empty finite or countable set and E is a subset of so this is a graph, okay? So the points that I drew here are the set V and are the vertices of the graph. And the lines that I drew here are the edges of the graph, and those are on this set E, which is a subset of this, okay? So V so let me write it. So the elements of V are called the vertices of G and the elements of E are called the edges of G. Okay? So these are just definitions in case you've never seen these definitions before. This is a graph, okay? So this is what we call a graph. So this is a graph, okay? This is the archetype of a graph. These lines here represent the edges, and the points represent the vertices. Graph, well, they have to be non-empty, because if they are empty, they are not very fun. They have to be, they could be finite or countable, okay? So uncountable is not good. And if 2 points are joined by an edge, we say that these points are neighbors. Okay, so you can have edges of the form XX, okay, and those are called the loops or the graph, okay. So remember that I drew a picture that looked like this at some point. Remember this picture? This picture was so there was it was a 1 here, there was a 1/4, 1/2, 1/4. So this picture here represents, no, this is what, no, the 1/4 was here. Here it was 1/3 and 2/3. So this picture here represented the probabilities of going from one distance to another distance on the plaza graph. And you can, if you forget about the numbers and the direction of the arrows, you get a graph like this. Okay, so this is a graph. It's an example of a graph. And this graph has loops. Has 2 loops. Okay? This one doesn't have loops. Because the guardian never stays where, at the same position. Okay? But if you look at what the guardian does in terms of distance to the center of the plaza, sometimes it keeps the distance constant. So if you want, this picture here represents how you choose this distance at each step. Okay? And these schematics here transform this picture into a graph which has less information, right? Because it doesn't have the numbers, but indicates some information of what happens with the graph. So graphs are just objects like this. So some examples, no? Bon, we have the plaza. So the Plaza de Armas and friends, no? So this is the Plaza de Armas. This graph here is what you see if you only look at the evolution of the distance to the center of the plaza. We have the simplified plaza. It's also a graph. And the simplified plaza also have another friend, which is so this is what you see when you look at the evolution of the distance to the center. There are only 2 distances, but so if you are at the center, you always go out. But if you are out, you can go in, and you can also stay put. Okay, so those are examples. Another very important example is the cycle. Okay, so let me write explicitly one cycle. So, well, this is a graph because I'm just listing the vertex set and the set of edges. And what is this? Okay, so this graph here is the following graph. It's a cycle with 5 points. Observe that these 2 graphs are equal. Okay? So actually what happens is that these 2 things are 2 representations of the same graph. Okay? Well, you can argue that maybe I should put points in these intersections here. I mean, these are just representations of a graph. The problem with graphs is that most graphs are not planar. Okay? So I'm going to give another example which is very popular. It's very important in computer science. It's called the hypercube. So you start with the number n, which is a natural number. Yeah, there is always this problem, no? People always ask this question, which is 0 a natural number? What is the answer to that question? Huh? The right answer is I don't care. Okay? Because this is just a symbol, and I can define this symbol as whatever I wish. So, in particular, I'm going to define this symbol to be the following set. Okay? And that's the end of the discussion. And now I define V. This set here, and I'm going to define E. As this thing here. Okay? What is this? So this is a binary sequence of length n. And I say that two binary sequences are neighbors if they differ in only one entry. That's my definition of being neighbor. Okay? And for n equals 2, this graph here is just this. It's a very, for n equals 1. So not a very interesting graph. For n equals 2, this graph is something that you should know is a square. Right? So this is 0, 0, 0, 1, 1, 1, and 1, 0. So for n equals 3, things get a little bit trickier. So we usually do this to draw this graph here. Okay? Actually, there is a better way to write this one. Which is this. These two graphs are actually the same. So, fun fact, not all graphs are planar, of course. You can have a lot of fun trying to draw n equals 4 on a piece of paper. Okay, so depending on how much time I have left on my lectures, I do it or not. So today, I won't. So planar graphs are graphs that, as the name indicates, can be drawn on a piece of paper in such a way that the edges do not cross each other. A very interesting thing is that a graph is planar if and only if it can also be represented as a convex solid. So this is a cube, and what we are doing here is that we are putting the camera of the cube very close to the center of one of the faces, and then what you will see is this. So this is something that you can do with every convex, how is it called that? Polyhedron. You have a convex polyhedron, and then you can bring a camera here very close to one of the faces, and you will have a ray of light uninterrupted to each one of the vertices. And then when you do the stereographic projection of that, so also called picture, what you get is a planar graph. So planar graphs, I just proved that planar graphs and convex polyhedra are in a one-to-one relation. So, but then, of course, for any equal 4, this is not the case, so you cannot do it in a piece of paper. And one of the main examples of Markov chains are random walks on graphs. So you draw a graph, and the first thing that you can do on a graph is exactly what we did with the Plaza de Armas. You put a guardian on the graph, and at each step is going to move to one of the neighbors chosen uniformly at random. So this is what we're going to discuss tomorrow. It's going to be our first example of Markov chain. It's called random walk on a graph. Okay. So let's stop for today. See you tomorrow. Ok. Os alunos do Impatec, por favor, fiquem um pouquinho agora para falar